Welcome back, everyone, to MAE170. This is lecture 2 in week number 1. So last time we saw an introduction to the course, and in particular, we saw the difference between open loop and closed loop control systems. The main difference being that in the closed loop control systems, we have a feedback portion that allows us to sense or measure the actual output and compare it to the desired output. So closed loop control systems are more complicated, but are also more reliable and flexible. If we take a look at the open loop and the closed loop control systems from the block diagram perspective, well, starting with the open loop control system, we have the input is fed into the controller, and then the control input is fed into the actuator, which then sends the signal to the process, and eventually we have the behavior of the system in the output. When we consider closed loop control systems, well, we have always the input, the controller, all the upper branch is the same. So we have the controller, the actuator, and the process. But now we have the ability to measure the actual output. So here I'm going to write it as actual output through the sensor. And the sense signal is then compared to the input, which for closed loop control system is also our desired output. And then we will see that the difference between the sensed output and the desired output is known as the error. But we're going to see that in detail later on. We also saw that the combination of actuator and process is known as the plant. And most of the times, we're going to consider the actuator and the process together. I apologize already. Sometimes I'll just call a process when I really mean plant, because we consider the actuator being part of the process, but it will be clear. So pretty much we'll have the plant and the controller that feeds the plant. All right, so that is these are, I should say, the general schemes for open loop and closed loop control systems. However, before designing a controller, we need to model the process. We need to know how the process behaves. In other words, how does the process transform an input to an output? So before starting to think about a controller, we have to think about, or we have to know pretty much into detail, how a process transforms an input into an output. So now if we take a look at our control systems, let's remove the controller part and the actuator for the open loop control system, and controller, actuator, and sensor for the closed loop control systems. And we only, therefore, consider the process, the performance of the process. So the ability of the process to turn an input into an output. How do we do that? Well, the process is described by dynamics. And dynamics, mathematically speaking, are characterized by ordinary differential equations. So the process can be modeled using ordinary differential equations. And once we have an input is just a function, can be of different types, as we will see. We can solve for a specific input the ordinary differential equations describing the dynamic of the process, and the solution of such ordinary differential equations, also known as ODEs in short, will give us the description of the output. We saw this in great detail in vibrations, but we will recall this relationship between input and output through ODEs. So now we have to review something about ODEs. So you should think about this lecture as a sort of a review of concepts that you should already know. And if you don't remember, don't worry. Again, we're taking the time to review them in enough detail, I should say. All right, so first of all, what are ordinary differential equations? Ordinary differential equations are equations that describe the rate of change of the output with respect to time as a function of the input, the output itself, and some parameters that describe the system. What does that mean, practically speaking? All right, let's take a look. Consider an input function, and usually in control systems, we indicate the input function with R. So R of t will be our input function as a function of time. So here in parentheses, we have t, indicating that this function is really a time function. What about the output function? The output function is usually indicated with y of t, or sometimes with x of t. It depends. It will be clear by the context. In this case, we're going to use y of t. I want to be faithful to the notation in your book. And also we have some system parameters. I'm just going to call it PAR, short for parameters. Can we have an example of a system modeled by ordinary differential equations? Yes, as we saw at the very end of last lecture, we can consider a mass spring damper system. So we have a mass connected by a spring and a damping element to a base. So we have M is the mass, then K is the spring constant, and we're going to call D the damping coefficient. So here we can have an external force as our input. So F of t will actually be our R of t. And the displacement of the mass with respect to its equilibrium point is the output, so y of t. Just gonna move it over here. Okay, so in this figure, we have everything that I described, the input being the external force applied to the mass. Then we have the output in terms of the position of the mass. And then the parameters being the value of the weight of the mass itself and the damping and spring coefficients. So the ODEs can be written as follows. We have a derivative of the output with respect to time, so the rate of change of the output with respect to time. We can write it as dy over dt, or more simply, y dot. So this is going to be a function of the input, of the output itself, and on the system parameters. All right, so this kind of equation is called an ordinary differential equation. We already saw it last time, so let's bring it back in this lecture as well. For the mass spring damper, we have a second order ordinary differential equations that can be written in this form. We have m times second derivative of the position of the mass plus d, so the damping coefficient, times the first derivative of the output plus kyt equals r of t. Or in a more compact form, we can write it as my double dot plus dy dot plus ky equals r. Why is it a second order ODE? Well, that's because the highest order of the derivative of the output is the second order, second derivative. We have, in this case, second derivative, first derivative, and the function itself. But the highest order of the derivative is the second order. So this is going to be a second order ordinary differential equation. The question now, once we have the ordinary differential equation that describes the model, in this case, the mass damping spring, we have to characterize such equation. The first question that we ask ourselves is the equation linear? In this case, it is. So how can we tell that the equation is linear? Well, there are a few things, but rule of thumb, you can check the following things. So first of all, the output and its derivatives have to appear linearly. So they have to have exponent equal to 1. And there shouldn't be any cross product between the function and its derivative, such as y times y dot. Or there shouldn't be nonlinear, such as trigonometric functions of the output and its derivative. For instance, if we had sine of y, sine is clearly a nonlinear function, so the ODE would also be nonlinear. The second question that we ask ourselves is the ODE time invariant? What does that mean? Well, a time invariant equation means that we don't have an explicit presence of the independent variable that is time. So in other words, time does not appear explicitly in the equation. Let's take a look at the equation in the compact form. There's no time that appears explicitly. So in this case, the equation is time invariant. If we had time appearing explicitly, then the equation would be named time varying. For instance, if we had my double dot plus dy dot plus kyt equals r, well, this equation would be always a second order, linear, but time varying. All right, so if our ODE is both linear and time invariant, sometimes you find this expression just LTI, that stands for linear time invariant. So why do we ask ourselves these questions? Well, because in this course, we're going to deal only with linear time invariant systems, okay? So if you had time varying systems, well, there's a whole new theory, or another, I shouldn't say new, but a separate theory that deals with time varying systems. And if we had a nonlinear system, well, that complicates things even more. There's already enough, trust me, that we can study for linear time invariant system. So that's all we will focus on in this course, linear time invariant system. Well, what happens if we had a nonlinear ODE? Actually, almost all systems contain nonlinearities. If you model pretty much all mechanical or even non-mechanical systems, there are always nonlinearity. So why do we want only linear equations, only linear systems? Well, there's a simple answer. Although most of the systems are nonlinear, they behave like linear systems locally. So around, for instance, an equilibrium point, nonlinear systems can be linearized. So if you start with nonlinear system, you can linearize them about a certain reference point. And you can use the linearized system and apply all the analysis that we will see later on in this course to the linearized system. And the approximation is quite good most of the times, only around the reference point though, because if you change a reference point, especially if the system is highly nonlinear, then the approximation wouldn't be good anymore. Let's take a look at an example of linearization. And this is a very simple example. As the name suggests, we're dealing with the simple pendulum. So I'm sure all of you are familiar with the simple pendulum. So we have a mass attached with a rod of length L to a pivot point P, and we measure the angle from the vertical, and we're going to call it theta. In this case, we can consider it positive when measured counterclockwise. And to simplify things even further, we assume that the only external force applied to the mass is gravity, so m times g. And of course, we have also the tension. I won't be dealing with how to retrieve the ordinary differential equations. As promised, I'm already giving you the ordinary differential equations that describe the behavior of the system. However, you should be able to retrieve such equations. You should be able to write them down, okay? Because you saw it in dynamics and in vibration. So, but for this course, I'll spare you that. So we'll just start with the equations themselves. If we neglect damping due to, for instance, drag with the air, then the equations are really simple. We have a second order equation given by theta double dot plus g over L times sine of theta equals 0. So assuming that there aren't any other forces acting on the pendulum, this is the ODE describing the dynamical behavior of the pendulum itself. Now, is this ODE linear or nonlinear? Well, it is nonlinear, and the nonlinearity is because of the presence of the trigonometric function sine of theta. Remember, the output, and in this case, the output is the angular position of the pendulum, cannot appear, or has to appear only linearly, and all its derivatives have to be linear. Y double dot is indeed linear, but sine of theta is not linear. So that's where the nonlinearity comes from. All right, so what should we do? Well, we have to linearize. First of all, though, we have to transform the second order ODE into a system of two first order ODEs. So in general, if you had an nth order ODE equation, then you will transform it into a system of n first order ODEs. So if you had a fourth order ODE, then you would have to transform it into a system of four first order ODEs. So how do we do that? Well, first of all, let's call the first derivative theta dot. We're gonna give it a new name, and we're gonna call it capital omega, and this represents the angular velocity of the pendulum. And therefore, if we take the second derivative of the angular position, well, that is equal to capital omega dot, and that represents the angular acceleration. So I'm going to go kind of fast here because these are concepts that won't be really, well, are useful, but either you've already seen them or are not going to be really key to this course. So I'm just going to go a little bit fast here. So now we have to find two first order ODE. The first one is simply the first equation that we already wrote. So theta dot equals capital omega. And now we can rewrite the ODE we started from, substituting theta double dot with capital omega dot plus G over L times sine of theta equal 0. Or if we leave the first derivatives on the left-hand side of the equation, we have theta dot and omega dot equals to omega and minus G over L sine of theta. So you see here that by transforming the second order ODE into two first order ODEs, we only have the derivatives, the first derivatives, but now we have two unknowns. And these two unknowns, theta and omega, are the so-called state vector. And when I use the square brackets, I refer to a vector. So we have a vector on the left-hand side that has to be equal to a vector on the right-hand side. So in this case, I'm just rewriting the system in this compact form, y dot equals f of y, where y is a state vector. And so y dot is equal to theta omega and, sorry, theta dot and omega dot. All right, so now that we have our system, we have to, well, we already know that it's not linear, but in order for a system of first order ODEs to be linear, well, it has to be, or it can be written in this form. It has to be written as y dot equals a matrix, a constant matrix, A times y. So A is a matrix. So formally, A belongs to the space Rn times n, and y is, both y and y dot are vectors, so they belong to Rn. So in this example, we have that y dot is equal to omega and minus G over L sine of theta. Clearly, this cannot be written as a matrix times the state vector because of the presence of sine of theta. So now what we're going to do, we're going to call the first line as f1, so a function of the state, so of theta and omega. And the second line, well, we're going to call it f2. And this is going to be clear in a second why I'm doing this. All right, so this is step number one. Starting from, in this case, a second order ordinary differential equation, we write a system of two first order differential equations. So that is step number one for the linearization in the proper way. Things could be done much faster, but this is, in my opinion, the proper way, because sometimes when things are done faster, some details slip and then mistakes are made. So I think it's safer to just use the longer route, but a clearer route, in my opinion. Okay, so step number two. Now we have to write the Taylor series expansion of the system one. So this is one. And as you know, the Taylor series expansion, well, it's an expansion that makes sense only when it is done about a reference state. So we have to pick a reference state. In this case, we're just going to call it y naught. So how do we write a Taylor series expansion about y naught? Well, that is equal to, so our y dot, that is f of y, is equal to the function evaluated at the reference state plus, now we have the first derivative of f with respect to y evaluated at our reference point times y minus y naught, and plus we have all the higher order terms. Or hot, H-O-T. Well, since we are linearizing, we only care about the first order. So that's why I didn't bother writing down the higher order terms, because what we're going to do is we're going to ignore the higher order terms and we're going to just retain the first order. So in other words, the linear approximation of a nonlinear system is the following, and we're going to call it FL for linear. So that is equal to the function evaluated at our reference point plus df over dy evaluated at the reference point times y minus y naught. And the partial derivative of f with respect to the state y, since f is a vector and also y is a vector, well, this is a matrix. It's actually a square matrix known as Jacobian. So let's get practical here and see actually what it means. So first of all, let's just choose a reference point for the simple pendulum example. And in this case, I'm going to choose the upward equilibrium. So if the pendulum pendulum could technically be balanced upside down. So since it's an equilibrium point, the angular velocity is 0. And what about the angular position? Well, the angular position is 180 degrees because we're measuring the angular position from the vertical downward position. 180 degrees is also pi radians. Okay, so now that we have our reference position, let's find the Jacobian matrix. So the Jacobian matrix is, its elements are all the partial derivatives of the function f with respect to all the states. So in this case, we have the first entry is df1 dy1. And then we have df1 dy2. And in the second row, we have df2 over dy1 and df2 over dy2. What are y1 and y2? Well, in this case, they're going to be equal to theta and omega. Just gonna move this up here. So actually, just to keep things, to introduce more notation, we can write it as directly theta and omega. Now you understand why I called the two functions earlier as f1 and f2. So now we can take the partial derivative of f1 with respect to theta and with respect to omega, and then do the same for f2. So f1 was omega, so the partial derivative of f1 with respect to theta is simply 0. There's no theta. And what about the partial of f1 with respect to omega? Well, that is equal to 1. What about f2? f2 is minus g over L sine of theta. So df2 d theta is equal to minus g over L times cosine of theta. And what about the partial derivative of f2 with respect to omega? Well, there's no omega in f2, so the partial derivative is 0. So now we can construct the Jacobian matrix. Can fill it in. 0, 1 minus g over L cosine of theta and 0. Now remember that this matrix has to be evaluated at the reference point. So we have to substitute theta equals theta 0. So in this case is pi, and omega is equal to omega 0, and that is equal to 0. So if we make this substitution, I'll just go down here. Well, we find 0, 1. Now, what is cosine of pi? That is minus 1. So minus g over L times minus 1 is plus g over L. And then the last entry is 0. So this is the Jacobian matrix for this specific reference point. Finally, we're ready to write down the linearized system. And we're going to do it in this fashion. We write it as theta y dot equals to our Jacobian matrix evaluated at our reference point, times delta y. What is delta y? It is just y minus y naught, and same thing for delta y dot is y dot minus y naught dot. Okay. So in our example, we have that delta theta dot and delta omega dot are equal to 0, 1, g over L, and 0, multiplying delta theta and delta omega. And this is the linearized system. Let me highlight one thing once again, that this linearization is only valid about the reference point that we chose. If we choose another reference point, then the linearized system would be different, okay? Now, if we want to go back to an ODE of a second order kind, then we can do the following. Using a little bit of abuse of notation, let's just write theta instead of delta theta and omega instead of delta omega. So now we can go back to a second order ODE, just kind of following in reverse step number 1. And we find that our linearized second order ODE is theta double dot minus g over L times theta equal 0. So you see here that this equation is obviously a second order equation. The order does not change, but now it is linear because we don't have sine of theta anymore. We have theta itself. Perhaps some of you would have just, starting from the original equation, which was this one, let me write it again. Some of you would have said, oh, okay, or because you were taught this way, the linearization is simply theta double dot plus g over L, and sine of theta, well, for small angles is equal to theta. So we have, there you go, this linearization here. You see that there's a problem, and that is the sign. With our longer process, we've obtained a minus sign. So how come that if we approximated sine of theta with theta, we have a plus sign? Well, that is because this equation here with the plus sign is valid for small angles. That means that the linearization is done about the downward vertical position, the downward equilibrium, not the upwards. So be very careful when you linearize equations. You have to be sure that you know the reference point. If you go back and redo all the linearization process following steps 1, 2, and 3, but now using the downward equilibrium, so we would have theta 0 equals 0 and omega 0 equals 0, then you would find the plus sign eventually. So again, be very careful because the linearized system depends on the reference point about which you linearize the original nonlinear system. All right. So with the linearization out of the way, now we assume if we have a linear system, good to go. If we have a nonlinear system, we'll linearize it about in an equilibrium point or a reference point. So now let's assume that we have a linear time invariant differential equations. that describe the process. So starting from the process, through modeling, we find the ODEs. If it's nonlinear, well, we'll linearize it and we find a linear equation. Okay, so now what do we have to do with an equation? We have to solve it, right? Okay. Ordinary differential equations are not that easy to solve, not that trivial. At least they're very, very difficult to do it analytically. But we have to find a way to solve them. So if we started from our ODEs and we are in the time domain, as we've been so far, in order to find the solution, y of t, well, that can be, as I said, a tricky endeavor. It's kind of complicated, such as, climbing mountains. You can get to the solution, but it's kind of difficult. So why don't we find a way around the mountains? We can do that. It's just a little bit longer. It involves another domain. We have to switch our main variable from time to this variable that is indicated with S. And it's also known as the Laplace a variable or complex frequency. We're going to see later what it means. For now, just trust me on this. We'll just almost magically switch to another domain. And we're going to do that through an operation that is known as the Laplace transform. So what we're going to do, we're going to take our ODEs, apply the Laplace transform, and these equations from ordinary differential equations will become algebraic equations. Algebraic equations do not have derivatives with respect to time. As a matter of fact, there's no time at all here. We are using only the S function. Algebraic equations are much easier to solve. So the solution is just like going on the straight road. Very, very easy. So we can find the solution in the S domain. We're going to call it y of S. And whenever we are in the S domain, we're going to use the same symbol, so the same y, but we're going to use just a capital letter. All right, so almost done, because, well, there's a thing about the S domain. It is easy to find the solution, but it doesn't really make sense, the solution, if we plot it. Or better, it would, but it's very difficult to interpret it. It's not intuitive. It's not intuitive, and it's not easy to understand. So we kind of have to go back to the time domain. For instance, if we want the position of the mass connected via a damper and a spring, well, it makes sense that we see the position as the time goes on. If we keep it in the S domain, again, it's counterintuitive. It doesn't really make sense, the solution. So we have to go back to the time domain. And we're going to use the inverse operation, which is known as the inverse Laplace transform. So that is kind of the logical path. We start with differential equations that are difficult to solve directly. So instead of solving them directly, we change domain using the Laplace transform, and we obtain algebraic equations. The algebraic equations are easily solvable analytically, and then we apply the inverse transform to get back to the solution in the time domain. So a little bit, 2 more steps, but overall it's going to be much easier. So just a review of what the Laplace transform is. Well, the Laplace transform of a function in the time domain is going to be written as the following. So we have y of S So that is the function in the S domain or in the Laplace domain is equal to, so we are going to use the symbol, this cursive L, capital L for, that stands for the Laplace operator. And so that is applied to the function in the time domain. Laplace transform can be applied only to linear systems because, well, the Laplace transform is a linear operator, and that's why we're considering only linear time invariant system, because the Laplace transform only works for linear time invariant systems. It's a very powerful tool, but we are restricted to that subset of problems. Again, that's going to be enough, trust me. But keep in mind that you cannot just apply the Laplace transform if you have a generic non-linear time variant system. You have to do other things. Okay, so as I said earlier, S is also known as complex frequency, so it's a complex number. So that's the complication, if you wish, because we start from the time domain and time is a real number, and we switch to the S domain where S now is a complex number. So complex number, and that's why I told you to review complex numbers, and that's the reason why, because we're going to do all our operations in the complex field. So a complex number has a real part, which will usually be written as sigma, and it will have an imaginary part. So we have I times omega, and I is the imaginary unit. And the definition of the imaginary unit is that if you take the square of it, well, that is equal to -1. So very quickly, what is the Laplace transform? We have a formal definition in terms of integral. If you have your function in the time domain y of t, and you want to find the same function, but now in the Laplace domain, you have to take this integral from 0 to infinity of y of t times e to the minus st in dt. And if you want the inverse, well, you have to solve an even more complicated integral. So some of you might ask, wait, you said that this is kind of longer, but it should be easier. So this doesn't look very easy. We have to solve integrals now. I mean, we could have just solved the ordinary differential equations. In the end, we still have to take integrals. So what's the point of having the Laplace transform? Well, the thing is, most of these integrals, you don't have to solve them. They've already been solved because we can use tables. Most of the functions that we will see are already tabulated. We already have the Laplace transforms for these functions. So we will never have to really compute these integrals directly. Let's take a look at some of these functions. So let's start with the simplest of them all, which is called the Dirac function or impulse function. So in the time domain, it's not really a function. The impulse is a little bit of a weird thing. It's defined as follow. It is defined as a function that has an infinite height but 0 width, but the area is equal to 1. It is a little bit weird. So just the way you should think about it, or at least the way I think about it, that it makes kind of sense. Let's say that you start with the rectangular function centered at 0, and the area of this rectangle is 1, and then you compress the sides so that the height of the rectangle increases, but then the area still remains 1, and then you compress it even more so that the height increases. And then if you take a limit of that, then you have the width goes to 0 and the height goes to infinity, but the area is still equal to 1. So this is an impulsive function. It's something like if you hit a baseball with a bat, you give it an impulsive force. You can also think about it as something that happens very, very, very quick, instantaneously, I should say. In the time domain, it is kind of difficult to define it, but in the S domain, in the Laplace domain, well, that is just equal to 1. Very, very easy. Well, if the impulse had, let's say, a height that is equal to k, then in the S domain, the transform of this function would be k. So you can multiply the input with the constant and the constant. Since the Laplace transform is linear, then the constant is just a coefficient that multiplies it. For now, let's just keep k equals 1. Second example, step function. Step function, also known as Heaviside function, it's just a constant function. You should think it as just a constant function. And if its height is equal to 1, then it is also known as, or indicated as, u of t, where u is the unit. So this is the step function. In controls, constant function is called step function. So in the time domain, it is a constant value. So u of t, if you just find u of t, that is just equal to 1. So it's not really a function of time. It's just constant throughout time. In the S domain, that is equal to 1 over s. Now, what if we had t to the power of n? Well, then that is transformed into n factorial divided by s to the power of n plus 1. For instance, if we had a linear function that grows with time, that is called a ramp function. Pretty self-explanatory. Well, in this case, we have y of t equals t. Let's say that the slope is 1. Then in the S domain, this becomes 1 over s squared. We can have a parabola, but in control, this is known as the acceleration function. And this is in the time domain, it is proportional to time squared. So if we just have time squared, then in the S domain is equal to 2 over s cubed. Then we have the exponentially decaying function. So e to the power of minus at. In the S domain, it becomes just a fraction, 1 over s plus a. Sinusoidal functions, harmonic functions, sine of at and cosine of at in the S domain become a over s squared plus a squared and s over s squared plus a squared, respectively. Another thing that is very convenient when we go from the time domain to the S domain is the convolution integral. So if we have a convolution between two functions, and the convolution mathematically is the integral from 0 to t of one function. Now, the variable is t minus tau times the other function tau in d tau. Well, this whole integral in the S domain is simply substituted by the multiplication, by the product of the two functions in the S domain. So the convolution between g and r of t in the S domain is simply the product between G and R. And lastly, the integral of y of t in dt is simply y of s over s. So every time that you divide a function by s, it's like taking the integral of the function. And well, I skipped this, but this is very important. It's the derivative. So the nth derivative of y of t is given by s to the power of n of y. And then we have to subtract all terms containing the initial conditions. Because whenever we have a derivative, well, usually we have again, an ordinary differential equations or an ordinary differential system of equations. And so in order to solve the ODEs, well, we need a set of initial conditions. So for instance, if we had the second derivative of y with respect to time, in the Laplace domain, this would be equal to s squared times y of s minus, now s times the y at 0, so the initial condition in terms of position, if you wish, minus the initial condition in terms of the initial velocity. So this is just an example, second order example. And then finally, as I said, the Laplace transform is a linear operator. So if you had a linear combination of two functions, y1 and y2, so a y1 plus b y2, the Laplace transform is going to be a times y1 in the Laplace domain, plus b y2 in the Laplace domain. Okay, so I'm just gonna finish here because I think this is enough for today. So I'm just gonna leave the example here. So please take a look at it. We will discuss it next time, but that's how you would actually solve an ordinary differential equation. And in this case, we're going to consider a mass spring damper going through the steps that we've seen. That is, starting from the linear time invariant equation, we transform it using the direct Laplace transform. We find the solution in the Laplace transform, and we apply the inverse Laplace transform to find the solution in the time domain. And to do so, we need to use another tool that I'm pretty sure you've already seen, but if not, we're going to review it. And it's called the partial fraction expansion. So I will, again, as I said, I'll stop here for today, and I'll go step by step for this example next time, but please take a look at it, okay? Because I will cover it. I just want you to have an idea. All right, this is all for today, and I will see you next time. Take care.